Hello. Today I will try to show that our universe can appear to be local, real and therefore logical. I perfectly know that the Nobel Prize in Physics in 2022 was given for establishing the violation of Bell inequalities. I'm going to show what exactly that violation means. You might be surprised. Many people think that Bell inequalities prove that our universe is not locally real. And some of them seem to think that they prove that our universe is both not local and not real. Even under one of my videos there are comments like this. As a physics major, well, almost actually, I can tell you that if you are looking for a local interpretation of quantum mechanics, you can't. I stopped the video when you said you wanted to find a local explanation. So people just stop thinking and watching as soon as they hear word local. As if it's cursed. It's really strange, because even Bell inequalities actually speak about locally real universe, not about local universe. What do professors teach those students if they don't see the difference? Do professors see the difference themselves? Let me explain. Bell inequalities include two assumptions. Our universe is real. And our universe is local. Based on these assumptions, predictions are calculated using classical theories and using quantum mechanics. Those predictions are checked in experiment and quantum mechanics wins. Okay. So what does it mean? It means that at least one of the two assumptions is wrong, either universe is not real or universe is not local. Not necessary, both of them are wrong. Universe can appear to be local and not real, or real and not local. Why on earth almost physics major would ever think that quantum mechanics cannot be local, I have no idea. The matter as machine model described on this YouTube channel is local. So if my assumptions are correct, Bell inequalities should be telling us something about universe not being real. What does the statement that universe is not real mean for quantum mechanics? It means that we cannot speak about properties of a particle like its position or momentum until it's measured. In popular science you can also hear that until its measured particle has no position or momentum at all. Until its measured particle exists only as some kind of wave described by its wave function. What does the statement that universe is real mean for quantum mechanics? It means that particle always has specific properties, position, momentum, even before it's measured. What does the statement that universe is not real mean for the matter as machine model I describe? It means that measurement is always some kind of interaction. Interaction unpredictably changes the state of the particle and we cannot know which state particle had before it was measured. As measured value describes not the original, but the changed particle. We know that particle can change its movement direction as a result of interaction. Diffraction is a good example of that. We cannot know in advance where exactly particle will be observed. We can only know the probabilities of observation for specific positions. But it also means that when we observe some particle, we cannot know the real position or state of that particle before the interaction, only probabilities for different positions and states. Therefore it seems to us as if particle has no any specific position or state before the interaction happens, as if the interaction defines its properties, as if until interaction happens, particle exists only as some kind of wave. Therefore it seems to us that particle is not real. But that does not have to be true. Interaction unpredictably changes the state of the original particle. This is the only statement that Bell inequalities really prove. But we already know that interaction changes the properties of the original particle. There are widely known effects in quantum mechanics that describe it. Heisenberg's uncertainty principle. Observer effect. In one of my previous videos I've explained the reason for the Heisenberg's uncertainty principle within the matter as machine model. In that video I've explained that according to my assumptions Heisenberg's uncertainty principle and observer effect describe different aspects of the same phenomenon, the discrete interaction of particles. Link to that video is in the upper right corner now. So let's extend that list to 3 effects. Heisenberg's uncertainty principle. Observer effect. Universe that looks as if it's not real. Let's shortly review each of them. Heisenberg's uncertainty principle. Particles exchange discrete pieces and energy of each discrete piece equals reduced Planck's constant, which according to my other video is actually not quantum of action, but quantum of energy that causes quantum of action. Link to that video is in the upper right corner now. Observer effect. Measurement is interaction and changes the properties of the original particle, therefore after interaction we get particle with new properties. Universe that looks as if it's not real. After interaction we get particle with new properties, therefore we cannot know the original properties of the particle. All these effects according to my assumptions describe different aspects of the same phenomenon, the discrete interaction of particles. Seems like modern scientific community somehow believes that these are three different phenomena and are not connected with each other. But let's face it, if we assume that our universe is local, all three effects are caused by the matter interaction. Why should they be different phenomena? Only because scientific community wishes so. Why the result of particles interaction is unpredictable in discrete world? Well, because it's discrete. You cannot know what will be the sequence of interactions. Depending on the sequence of interactions, result can be very different. Let me demonstrate that using the popular conveys game of life. First we generate equal initial states in different parts of the universe and launch the game. We get the same sequences of actions as result. Both gliders interact with other figures the same way. Now we slightly update the initial state of one of gliders and check what happens. We get absolutely different results. Why? Well, because game of life is discrete and each discrete state depends on the previous discrete state very much. Does the fact that results of interactions are different for slightly different initial conditions mean that game of life is not locally real? No, it does not. Particles always have exact state and exact location, and interaction happens not faster than one cell per move. Not only game of life is locally real, it's predetermined. Predetermined, but not predictable. You cannot predict the result for specific more or less complex initial state of game of life other than by launching it and checking the result. So according to my assumptions, the only thing that Bell inequalities really prove is unpredictability of our universe. Particles with different initial states can cause the same measurement results and therefore can look like a wave of probabilities for observer. Therefore we get additional unpredictability after each measurement. And because of that we cannot gather statistic for Bell inequalities. Specifically we cannot gather statistic for classical theory. Because in classical theory it is assumed that measurement does not change the particle state. As we cannot gather statistic for classical theory, we have nothing to compare in Bell inequalities. Therefore Bell inequalities cannot be used. The simplest example is a polarizer. It is an optical filter that lets light waves of a specific polarization pass through while blocking light waves of other polarization. This explanation is taken from Wikipedia. Very important detail should be added. All the light that passes through the polarizer also changes its polarization to specific predictable state. So after light passes through the polarizer we do not have original photons, we have polarized ones. Information about the original polarization of photons is lost and therefore looks like a wave of probabilities for us. In classical theories it is assumed that we can measure the original polarization of photon, but we can't, therefore we can't calculate classical predictions. And cannot use them in Bell inequalities. The same way we cannot use them for any other experiment, which as they say prove quantum non-locality. If we ignore the fact that particle state is changed by interaction or measurement, we get paradoxes like the so-called three-polarizer paradox or quantum entanglement and spooky action at a distance. Let's review the so-called three-polarizer paradox briefly. If we use two linear polarizers oriented at 90 degrees to one another, no photon can pass through the system. Every photon that passes through the first polarizer gets polarization axis oriented perpendicular to the axis of the second polarizer. These photons just cannot pass through the second polarizer. Why? Maybe we will know the answer when we get the theory of everything. So far it's just a fact from physics. But we can add third polarizer, oriented 45 degrees to both polarizers. If we put it in between the first and the second polarizer, some light will pass through the system. Why? Because the added third polarizer changes the polarization of photons that pass through it. After that, some photons can pass through the last polarizer. Only if we ignore the fact that polarizers change the original state of a particle, we get unexplainable paradox. Let's also show analogy from classical world. The ball will stop its movement in the first case, but will continue movement in the second case. Would you call it paradox? The proposed model physicists would call a theory with local hidden variables. They say that such theories are ruled out by Bell inequalities. I can't agree. The difference of the proposed model is that local hidden variables exist only until the first interaction or measurement happens. After that, local hidden variables disappear or partially disappear. Let's review one of experiments that were used to test Bell inequalities. Photons with local hidden variables are emitted by the source. Local hidden variables exist until photons pass through the polarizer. Statistic is gathered after that. So how classical statistic can be gathered? Local hidden variables do not exist by that moment. State of particles we measure is changed by interaction with polarizers. Therefore there is nothing to gather and nothing to compare in Bell inequalities. Let me demonstrate it another way. Let's assume that we want to catch a quantum criminal who has escaped from quantum prison. Let's assume that there is only one way out of prison that quantum criminal can use. We put a filter that should observe quantum criminal as he approaches. But as quantum criminal passes through the filter, he can turn into regular quantum citizen with some probability. Or even worse. Regular quantum citizen can turn into quantum criminal after passing through the filter depending on experiment setup. What classical statistics we can speak about in this crazy situation? How the discreteness of proposed matter as machine model leads to unpredictability, which we call randomness? Actually, it was already described in the video about the Heisenberg's uncertainty principle mentioned above. Watch it for more details. In short, we cannot know which exactly discrete piece will be passed from one particle to another during interaction, and therefore we cannot know how states of particles will change as result. We can know only the probabilities of what can happen. Just to sum up, if my assumptions are correct, then the only thing that Bell inequalities really show us is that the truth is unknowable. The past is unknowable, the future is unknowable. Everything we have is now. But our actions do affect our future. Either it's predetermined or not. At least something definitely depends on us. For example, now it depends on whether you press that like button. If it's true that our universe is local, real and logical, I think people should know. Even if there is only a slight possibility to get the answers, we should try. I should also mention that in one of my previous videos I've proposed alternative postulates for special relativity and proposed experiment to check them. If such experiment is ever launched and if it confirms the predictions, it would mean that Albert Einstein was wrong when he assumed that the speed of light does not depend on the speed of observer. Link to that video is in the upper right corner now. But at the same time, if my assumptions are correct, Einstein was absolutely right when he refused to accept the fullness of quantum mechanics. Quantum mechanics is not full, it does not describe reality, only its probabilities. Randomness appears in it because we don't know, and cannot know, the initial state of the system. Future of the system is predetermined, until random event happens, if random events exist. But even though it's predetermined, it's not predictable. It's really interesting that historians of science call Einstein's attitude to quantum mechanics Einstein's biggest mistake. Yeah. His biggest mistake was to be right. To not agree with scientific community. Therefore, you don't have to be right to win. You don't have to be wrong to lose. Seems like humans love paradoxes. Much more than truth. Paradoxes are mind-blowing. Truth is boring. Unfortunately, paradoxes have higher chances for survival. Just like our favorite pets. That's why science is still full of paradoxes. Thank you for your attention.